right, so let's go ahead and get started. So welcome to the Friday Physics Colloquium before Halloween, hence the costume. So it's my great pleasure to welcome today's speaker, Dr. Nathan Inan of Close Community College, and also Fresno State. And actually, as I asked him if he doesn't mind to include Fresno State as his affiliation on his publications, of which he has several from this past year. So if you're interested, actually some of this talk is going to be about the work from those publications. So Dr. Inan, like I said, is currently in Close Community College and also teaches here. He did his undergraduate at Cal State Long Beach, then did his master's degree. We were fortunate enough to have him do his master's degree with us. And then he went on to UC Merced, where he worked with Ray Chow. Some of the research that he did there is going to be in this talk, and the title of this talk is Inertia and Propulsion from the Gravitational Field of the Universe. Nathan, take it away.
Thanks, guys. Thank you so much, everyone, for having me today. I'm super excited to give this talk. And I hope you don't mind, I'm going to have this stick in front of my mouth most of the time because of our friends on Zoom will be able to hear me more effectively that way than if the mic is far away from me. All right, so thank you so much for the introduction, Doug. I appreciate that. As he mentioned, the title of this talk is Inertia and Propulsion from the Gravitational Field of the Universe. Technical difficulty already. I might just stay close to the computer and click off of it directly. Oh, there we go.
You try to do the remote control clicker?
Yep,
Okay.
found it. Let's see what that took care of it was. Maybe not. All right, well, I'll just click off the computer anyways. Oh, you know what? It's the PowerPoint that wasn't live.
There you go.
There we go. Great. All right, so we're going to look at a brief history, talking a little bit about Einstein, Shiyama, and a few others who address this topic of inertia and, by extension, propulsion. We'll look at current interest in inertia and propellantless propulsion, which is kind of a hot topic. No pun intended. Propellantless topic. You're going to have to mind my corny jokes along the way, by the way. It's just part of who I am. So two scientists are building a real Star Trek impulse engine, and that's in fact Jim Woodward and Hal Fern. I'll show you a little excerpt from a video that you might have already seen from theirs. As Doug mentioned, it's become pretty popular. It's in fact hit over over 1 million views. Then we're going to look at results from a paper that Lance Williams and myself wrote, referred to as linear inductive frame dragging. And we're going to look at just general relativity and the RW cosmology model and see if, in fact, inertia and propulsion are predicted mathematically from those theories. Lastly, I'm going to connect things back to Shiyama and Hubble Expansion. So the whole idea then is that Shiyama was a key figure many decades ago in this topic. And what I'd like to do is connect what Lance and I have done back to what Shiyama formulated. Shiyama did not use a metric theory of gravity. He did not use general relativity, and yet his work is referenced a lot. So I thought making this connection here would be important as sort of a top-off of our talk, and it might open up the way for a little bit of controversy, which never hurts, a little bit of debate at the end of our discussions. All right, so I'd like to do a little bit of a review about the contrast between Newton's laws of gravity and Einstein. So as you probably are, or as you may be aware, Newton's law of gravitation is expressed in this equation here, which tells us that gravitational force is related to two objects that have mass, say an object with mass capital M and an object with mass little m. And the main point here is that space and time are essentially just like a backdrop. So what happens is all the dynamics, all the particles and motion of objects and things like that happen within space and time, but they don't affect space and time. In contrast to that, Einstein's theory of general relativity, which also includes Newtonian gravity but goes beyond it, shows us that actually mass and energy can warp space and time. And so as a result of that, there's a lot of ramifications that come out that alter our understanding about how the universe works. I'd like to mention a few of the things that make us convinced that general relativity is in fact the correct theory of gravity as far as matching up with all the experiments that we've seen or observations that we've seen. First of all, Newtonian gravity predicts that light's not affected by gravity, while general relativity, on the other hand, predicts that light is in fact bent or curved by the presence of gravity, or in other words, curved space-time. So what that means is that if there were to be like a star on the other side of the sun from the Earth, according to Newton's law of gravity, you wouldn't be able to see that star because the light from the star would just pass right on by like so. But according to Einstein's theory of general relativity, space and time are curved or warped or bent in such a way that light follows those curves, and so we can in fact see this star that otherwise would be behind the sun, and that was in fact observed experimentally. We also have the precession of Mercury's orbit, which is known to be, you get an incorrect result if you attempt to use Newtonian gravity, but if you use general relativity, you get the correct result for the precession rate of Mercury's orbit. There's also what's called gravitational lensing. There's actually a whole assortment of phenomena that general relativity predicts that Newton's law of gravity would not predict. Gravitational lensing involves basically if you have something like, say, like a galaxy here, and behind it you have something like a quasar, and the light from the quasar will bend around the galaxy like you see there, and there's a number of interesting phenomena that come out of that, like for instance Einstein's cross is one example of that. There's another one called Einstein's ring. I started thinking like all these Einstein objects out there, crosses and rings, and it seems like a jewelry store practically. Here's the Einstein ring for you. And so all of these phenomena are predicted by general relativity. Now one aspect of general relativity that I personally find the most interesting is that you can cast the gravitational fields in a form that look a lot like electromagnetism. So just as we have an electric field in electromagnetism, we can speak of a gravitoelectric field, which is pretty much the gravitational field you're already aware of that holds your feet to the ground, for instance. But then there's this extra guy here, this gravitomagnetic field that otherwise wasn't predicted by Newton, but is predicted by general relativity. So the Earth, for example, because it rotates about its axis, essentially kind of swirls the space and time around it. It's almost like you can picture it like a whirlpool type motion, sometimes called frame dragging. So that is in fact related to the paper that Lance and I wrote, except we weren't looking at rotational type situations, we were looking at linear motion, which I'll get to a little bit later. But there is an experiment, Gravity Probe B, that in fact verified that this frame dragging or lensitarian field is a real thing. And then we have, of course, black holes. I think many of us, or probably all of us, have heard of black holes, again predicted by Einstein's theory of general relativity. And then we have a personal favorite of mine, gravitational waves. And so Doug mentioned that I did research with Ray Chow up at UC Merced, and that was the primary topic that we were looking at, was gravitational waves and how they interact with superconductors. And so again, that's something that's predicted by Einstein's general relativity that would not be predicted by Newtonian gravity. And so this was observed first by the Hulse-Taylor pulsar, was a way that gravitational wave radiation was calculated and then confirmed to match up with Einstein's general relativity. And then in the more recent news, I think it was, I believe in 2014, the Nobel Prize was awarded for the observation of gravitational waves at LIGO. So we have two observatories in the United States, one in Washington and one in Louisiana, and they've actually made multiple observations. This is some data coming from the fourth observation, but this is just to demonstrate the fact that general relativity has such a huge scope of explanations for phenomena in the universe. So this brings us now, actually I'd like to mention one more interesting ramification of general relativity, because sometimes people think, oh, this is all just AC spacey stuff, it doesn't apply to us. But actually GPS, the GPS system that you use in your vehicle, relies on calculations that are performed using Einstein's general relativity. So you'll notice here that time runs faster because of weaker gravity up in the where satellites are. And so there's a correction that's needed for the time that it takes for light to propagate, or in other words, the signals that you're receiving from the satellites there. And believe it or not, if those corrections weren't done by general relativity, we would not be able to navigate the way that we do with our GPSs. So this is a very real thing. Now we come to the topic that is most pertinent to this particular talk, which is the cosmological expansion of the universe. So it's modeled as a Big Bang that occurred. We Probably most of us have heard that terminology, and I'm not going to go into all the details of the cosmology itself related to the Big Bang, other than to just say that we know that the universe is expanding, and in fact it's expanding at an accelerating rate. That was also something predicted by Einstein's General Relativity as well. And so we call this Hubble Expansion, which I'll refer to a number of times during our talk. So you can kind of picture it like this. All these galaxies here, if you kind of imagine they're like in a raisin bread and you're heating up the bread and it's expanding out, then all these galaxies are expanding out from one another. And so the universe as a whole is expanding. In fact, technically speaking, even in this room, that expansion is occurring. It's just so tiny that we can't perceive it, or generally we assume we can't even really detect it experimentally either. But when we look out in the cosmos, we can see evidence that it's in fact occurring. Now, the question comes to bear, as the title of the talk, inertia. Can general relativity explain inertia? And in case you're wondering what is this inertia, well, look at Wile E. Coyote. Wiley's trying to push this rock here and having a hard time to do so. And the reason is because even though Wiley applies some force here, because the rock has a lot of mass, Wiley doesn't get much acceleration out of it. And that's essentially a measure of inertia. So that rock has a lot of inertia, so it's hard to get it to start moving. Now notice also, do you see how Wiley is kind of getting pushed back off the rock in a sense when he pushes onto it? And so that's in a sense a demonstration of Newton's third law, equal and opposite action-reaction forces. So when Wiley pushes on the rock pushes back on Wiley. And this is what has led us to wonder, can we get propulsion out of our understanding of inertia? Because if we understand how inertia works, and we can essentially like push off of, say, the gravitational field of the universe, then perhaps we can be propelled by it. So this is obviously just a cartoon model of the idea, but we're going to get into the thick of it as far as what general relativity would predict. So, in case you've never sat and looked at the universe, you should sometimes, maybe go camping, check out the stars. And the whole idea here is this, is that there's a whole lot of mass energy out there in the universe. Billions upon billions of stars out there. And so, is it possible that all of that mass energy that's out there in the universe, is it possible that it's interacting gravitationally with us in such a way as to explain why there is in fact inertia? And if in fact that's the correct explanation, that inertia is due to the gravitational field of the universe, then the next question is, can we somehow develop a way of propulsion by kind of borrowing from the momentum of the expanding universe? So it's all tied in together. You've got the gravitational field of the universe. Clearly, due to its expansion, there's an energy momentum out there. And the question is, it's sort of like a reservoir. Like imagine it like a huge reservoir of energy out there. And what we're trying to figure out is, can we tap into that and borrow some of it to propel ourselves? So I'm going to start with a little bit of basic math, just to kind of give all of us a little bit of a sense of where I'm going with this. But of course, forgive me if I lose some of us along the way. It's just the way it goes at a theoretical physics talk. So many of us are probably familiar with the Pythagorean Theorem, that if you take x squared plus y squared, you're going to get s squared, which is what we call an invariant. Because you can change x and y all you want, but as long as they are in this right triangle, then this s squared will always remain the same. Now you can extend that to 3 dimensions, bring in a z-coordinate, and then generalize the Pythagorean Theorem to 3 dimensions like so. So now you've got your x squared plus y squared plus z squared equals s squared. And then if we want, we can bring in one more dimension. What's the only dimension that's not included here so far? Time. So we can bring in the dimension of time, and when we do that, it's kind of interesting. It comes in with a minus sign. So now we've got our 3 dimensions of space and our 1 dimension of time, and it turns out that it leads to what we call a light cone that we exist in, essentially. And this is kind of the bare basics of special relativity, which will lead us into general relativity. So take this invariant guy here, and let's write it now in terms of a matrix. So notice that you've got these coefficients, -1, +1, +1, +1. Let's put those on this diagonal right there. And we're going to call this thing here, this matrix that you see, the Minkowski metric. And so you'll notice then that this eta mu nu, where mu and nu, these Greek letters here, are going to tell us which of these elements we're looking at. So the 0, 0 element is -1, and then any of the spatial elements are +1 for our Minkowski metric. Now the reason I'm taking a little bit of time to discuss this slide is because we're going to see this G here appear quite a bit throughout this talk, and I thought it'd be nice if we at least all have some sense as to what that thing is. And so this G00, again, think of it as like this term right here, which basically multiplies your time dimension, and this Gij is all this stuff in here which multiply your spatial dimensions. So now you have a way of stretching and compressing time and stretching and compressing space. Because if you just simply alter these G's here, you can achieve that. So if you want to think of it like back with the GPS satellite thing, we were talking about how time runs faster up where satellites are. That has something to do with this G00, for instance. Now what we can do is kind of picture it like the Minkowski metric is this flat space-time metric that you have here, where everything is just kind of uniform and isotropic and homogeneous. And then what you can do is you can allow these G's to be spatially and temporally dependent. So they can depend on space and time, so you can warp the space and time around you. Now the equation of motion in linear theory basically just says this. We're going to pretty much consider this G mu nu to be pretty much flat, but with just a little bit of a perturbation. So we're just going to introduce a little bit of gravity in a sense there. Now when we do that, the interesting thing about that is that you can get general relativity to look a lot like electromagnetism. So I thought this is a nice starting place, especially for those of us who are more familiar with electromagnetism, because you'll notice you've got this scalar potential piece and this vector potential piece. And you find that the equation of motion takes on this form here. And just to make the connection with electromagnetism, you see here these two guys right there. You've got your gradient of the scalar potential and your time derivative of vector potential. That's what we, of course, ordinarily identify as your electric field. And then over here you've got this V cross del cross of a vector potential, which you can also look at as a magnetic type field. Now you've got other stuff in here that goes beyond electromagnetism. So this red, I put them in red here because we don't see that one in electromagnetism. And it's a piece that's actually inside the time derivative on the left side there. You can pull it over to the right if you'd like and just recognize that it's essentially just an additional force term. And there's well more beyond that as well. But for now, this is actually helpful to look at in itself, because this is related to what's sometimes referred to as Einstein 1, 2, 3. And when I first heard that, I thought, oh, that's so cute. It's kind of like one of my ABCs and my 1, 2, 3s. And, you know, so this is our Einstein 1, 2, 3. This is our Einstein 1. And by the way, we didn't make this up. Lance actually familiarized me with this first because I was not aware of this. But evidently this Einstein 1, which is this red bubble here, was one way of attempting to explain inertia, which is basically the idea is, as it states here, the inert mass is proportional to 1 plus phi, and therefore increases with ponderable masses approaching your test body. So the whole idea basically was that when you approach some test body, that's when your inertia or your mass becomes relevant. It starts to affect your motion. Now, Einstein 2 is sometimes called an inductive inertia effect because of this time derivative here. And as it states, there is an inductive action upon accelerated masses of the same sign upon the test body, and Shiyama's paper was focused on that particular term right there. Einstein 3, which is this kind of like magnetic-like field, you could think of it as. We have here a material particle moving perpendicular to the axis of rotation inside a rotating hollow body is deflected in the sense of the rotation as shown by tearing from the lens of tearing field. So Ciuffolini and Wheeler are the ones that wrote most on this one here. And so these are just these are the only three that I'm aware of, in fact, of the ways that the force equation or equation of motion in linearized general relativity can be used to try to explain inertia. Our focus today is going to be primarily on the green one. Green's my favorite color, so of course that ended up being the green one. So we're going to focus pretty much on the green one because I'm most interested in Shiyama, and in fact it's the most connected to Jim Woodward's work, which we'll look at a video that we mentioned at the very beginning of our talk, and it turns out to be directly related to Hubble Drag. In other words, the cosmological expansion that I was talking about earlier in our talk. So I'd like to mention a little bit about Shiyama's paper. And this was back in 52, 53 that Shiyama wrote this. And I'm just going to highlight a few items in here. So Shiyama writes, as Einstein has pointed out, general relativity does not account satisfactorily for the inertial properties of matter, so that an adequate theory of inertia is still lacking. This paper describes the theory of gravitation which describes inertia to an inductive effect of distant matter. Notice also, he states outright that thus in this theory inertial effects arise from a gravitational field of a moving universe. For simplicity, gravitational effects are calculated in flat spacetime by means of a Maxwell-type field equations, although a complete theory of inertia requires more complicated equations. So he acknowledges that he's going to write something down that's not formally derived from general relativity, but if in fact it may lead to the correct explanation for inertia. So what Shiyama writes down, this is something that some of us here, especially on the Zoom meeting, have looked at many a times and scrutinized over, which is that you can write down essentially the scalar potential of the universe here as it relates to the mass density of the universe and the age of the universe, that tau there. And you'll notice that what Shiyama is saying is essentially this, is that this scalar potential is like a gravitational potential field that exists throughout the entire universe. And what he's going to say is, what if we start moving relative to this scalar potential of the universe? What will we observe? So he's saying that we're going to move with this velocity v of t, and in a sense then what will happen is that the universe will be observed as moving with the velocity in the opposite direction. So if that's the universe over there and I start walking in this direction, that's my velocity, it's the same thing as observing the universe as if it's coming toward me with the velocity in the opposite direction but the same magnitude. So that's what he's talking about here in this paragraph. And what he says then is that we're going to observe a gravitovector potential, like I was talking about earlier. It's kind of like related to the magnetic vector potential. And notice that it's related to the sort of like a mass current. This rho times v is like a mass current in there. And so what he concludes then is that you can arrive at this expression here, which is that the vector potential is proportional to that velocity with this prefactor of phi over c appearing there. And what he's going to argue is that this partial a partial t is going to effectively be the explanation for inertia. So I think that's a nice little segue, so that at least for those of us who are thinking about this mathematically, those are kind of the ideas that you want to have floating around in your mind as you take a look at this video that I'd like to share. So thank you, Jim, for giving us permission to share this at the talk. Of course, it's public, it's on YouTube, it's on the internet and such. And so it's titled here, Two Scientists Are Building a Real Star Trek Impulse Engine. And I might mention that on YouTube, at least as of last night, we had 1,225,403 views and almost 4,000 comments there already. So it's obviously a pretty popular video. It's a really cool video, actually, and I wish I could play practically all of it, but then I'd eat up 15 minutes of my precious colloquium time. So I have to be selective and share with you maybe just a few minutes from the video that I think is pertinent. And there's two spots in the video that I thought were interesting. I'm going to start at the very beginning and show us a couple minutes, and then I'm going to jump into the middle section of it and then interrupt it there.
Time for adventure!
I love this thing.
With conventional fuel rockets, it would take 15,000, 16,000 years to get to the nearest star. Conventional kind of rockets are just out of the question for interstellar travel. You're going to have to do something a little bit more out there.
So the half impulse.
With one half impulse.
What we're trying to do is build an impulse engine, like you hear on Star Trek. We'd like it to go at about 0.4 the velocity of light, just so that we can get to the nearest stars within a human lifetime.
Pretty modest, right? For the speed line.
There's no burnt up fuel, there's nothing being shot out of the tailpipe, and it's the gravitational field that actually will propel this thing forward.
This is the Mach Effect Gravity Assist Drive, a device that could make interstellar space travel possible. But the Mega Drive, as it's known, is also a design that hinges on some pretty controversial physics.
For many years, you work on a project that people think is nuts, and you're likely to be regarded as nuts too.
Now, after 30 years of
Don't worry, Jim, we don't think you're nuts, I promise. But we are going to analyze the idea of inertia from general relativity. I'd like to jump to another part of the video.
The way you think about it, If you look in a textbook, you might find 5 or 6 different definitions of Mach's principle. But the one I'm thinking of is that distant matter way out there can influence things up close.
To get your head around it, take this old analogy used to illustrate how matter bends space-time. If you put a heavy object on a trampoline, it falls in and curves the rubber sheet. Now, if you roll a ball on the trampoline, it will keep orbiting the heavy mass in the center. That's how a planet behaves when it's attracted by the gravity of a star.
The thing is, for the rubber sheet to act that way, it has to be under tension, it has to be stretched. And we're saying that basically the distant matter in the universe is what's pulling the space-time and making it taut. And that's what's causing it to act like basically like a rubber sheet.
The stretched rubber sheet is loaded with potential energy, and according to the team's understanding of the Mach principle, so is space-time.
So we're thinking that there's a big gravitational potential out there, and this device can actually tap into that. Imagine the space-time of the universe as being like a very, very flat lake, and you're sitting in a rowboat, the kind that has the seat that moves backwards and forwards, but you don't have any oars. Instead you have 2 great big buckets like big trash cans.
While you slide forward in the seat, the mass shifts around and the boat moves slightly. That's conservation of momentum, another Newtonian law. If there are no external forces acting on a system while it's moving, its center of mass has to stay in the same spot. And so the boat is moving to compensate for the different distribution of mass.
And what you're going to do is you're going to dump the buckets into the water, which is the universal space-time. And now you're a lot heavier than you were. Now you're going to slide back in the seat. And as you slide back, the boat is going to move under you so that your center of mass remains in the same spot. The boat actually moves forward as you slide back in the seat. Then you could dump out the water if you don't need it anymore, and then you repeat that process.
The megadrive works in a similar way. The part which is doing all the work is a stack of piezoelectric crystals, the same kind of material that's in your electric toothbrush. When you apply a certain frequency of electric current, the crystals expand and contract, which causes the whole device to vibrate. But the megadrive is set up to vibrate mainly in one direction, which causes it to accelerate slightly. The team says this acceleration enables the device to tap into the gravitational potential of the universe. By borrowing some of its energy, the crystals change mass and the device starts behaving like our rowboat.
That mass change is what's causing the propulsion, because each crystal kind of moves in this sort of fashion, so the whole stack is in this breathing mode, which moves backwards and forwards. As it gains energy, it increases mass, and then it shrinks again and loses mass. If you time it just right, you can actually make that thing move forward.
I love how they mentioned that it's like what we have in a toothbrush, because I'm like, really? Piezoelectric in a toothbrush? All right, so hopefully that gives you a bit of a visual as to what we're talking about here, as to what inertia is and what propulsion is, and it's an excellent video. Thank you, Jim, again for allowing us to talk about your video. So I'd like to get into some of the nitty-gritty as to what we found, Lance and myself, when we were working on this topic together. We recently published this paper, Inductive Rectilinear Frame Dragging and Local Coupling to the Gravitational Field of the Universe. And the summary here is actually very nice. It's a simple summary. So we have the cosmological drag force on moving bodies can be understood as inductive rectilinear frame dragging and represents a local coupling to the gravitational field of the universe. It implies that cosmic expansion can hypothetically be measured in a lab. So I'll give you kind of the punchline before even getting into the nitty-gritty. What we discovered is mathematically, just working from general relativity and Robertson-Walker metric, which is the standard metric for cosmology, there is in fact a coupling that you can have between test masses and the gravitational field of the universe. So you really can interact with the gravitational field of the universe. The downside, unfortunately, is that we found that it tends to be dissipative. So you only lose momentum to the universe. You can't gain momentum from the universe. Any question out there?
An obvious analog is when a spacecraft picks up speed by stealing a little bit of angular momentum from a planet in a planetary swing-by maneuver.
That's absolutely right.
So this is not a violation of the second law of thermodynamics, which I was going to give you a hard time about.
Thank you. I knew you'd give me a hard time somewhere. But yes, you're absolutely right. It is like the slingshot effect. In fact, it's interesting you mentioned that. So Dr. Ringwald was mentioning that this is a lot like the slingshot that you can have when a test mass is moving around, say, like a planetary body. And it's interesting you mentioned that because we did do an extension of this work where we attempted to look at something similar to that, where we were looking at kind of like a tractor effect, where you could in fact use the gravitational field of something that's a Schwarzschild type distribution, like a planet, and see if somehow you could get some kind of propulsion out of that as well. So it is absolutely all related. In this particular paper, our focus was specifically on looking at the RW metric. So again, just to remind you, going from the Minkowski metric and going to a generalized curved space-time metric, so you want to picture it now that these G00 and Gij, that they can be involved in causing stretching of the space-time of the universe. So specifically for the Robertson-Walker metric, we find that it looks very much like the Minkowski metric, except you just have this time-dependent parameter here in the spatial part of the metric there. And what you find then is that Hubble's constant turns out to be the time derivative of that scale factor divided by the scale factor. And this is all just standard textbook cosmology. And if you just, again, take standard textbook geodesic equation of motion, and you work out the connections, so you think of these Christoffel symbols as telling you basically the forces that you can get, and think of this as your acceleration. So this is just like a glorified Newton's second law, if you want to think of it that way there. So now these Christoffel symbols or connections can be evaluated using the metric, and there's a bunch of yucky math that goes into this process, but I'll just mention that the two non-vanishing Christoffel symbols turn out to be these two guys that both involve the Hubble constant that you can see there. And what you end up finding when the dust settles is this turns out to be your equation of motion. So again, think of that as like a Newton's second law. You've got an acceleration here on the left, and on the right you've got causes for force. And this is what is often referred to as Hubble Drag. And this is an additional term that's also kind of draggy, if you will, because notice that it's got a minus sign, it's got a Hubble parameter, and it's basically just third order in velocity there. Now, you might notice that since both terms are negative, then momentum can only be lost. So that's already kind of giving us, unfortunately, a bit of a red flag in going in this direction, because we're not finding anything that is providing momentum, only losing momentum. Yeah?
So for the Robertson-Walker metric, you're assuming spatially flat, right? So not curved positively or negatively.
You're absolutely right. K equals 0, I should have mentioned that. Thanks for mentioning it, Doug. It's K equals 0, RW metric there. Like you said, flat in the sense of the K curvature. Obviously not flat in the sense of Minkowski, but yes, that's exactly right. Yep. Now, it was interesting. It was brought to our attention by a colleague, Jose Rodal, who I greatly respect. He does a great job at scrutinizing our work, and I've always appreciated that. And he brought to our attention that Professor Edmund Birchinger, who I was already very familiar with his work, he's got some notes on cosmological dynamics, and his work is pretty thick, as you can see. Have fun sitting there. That's just one of like 90 pages or something. But so Jose pointed out to us this one spot. I think I highlighted it right there, which is that Hubble drag was referred to as merely a fictitious force. So all that we did there was all fictional. And we wondered about that. Well, wait a minute, how can it be fictional when we know the universe is in fact expanding, and there's ways to demonstrate that? And so this led us on a little bit of a wild goose chase. Is there a question about it?
Yeah, you're not supposed to say, ever since Richard Feynman made fun of it in the Feynman Lectures of Physics, delivered in the 1962 to 1963 school year, we've been told you're not supposed to say centrifugal force because it's only a fictitious force.
True.
But when you're a 6-year-old kid seatbelted into the backseat of your dad's car and he takes a right turn, it seems
sure
real
feels
enough.
like it, right? Yes.
So I think it's just a case of poor terminology.
You're absolutely right. That is absolutely right. So,
Yeah.
so Dr. Ringwald is mentioning that this is a lot like centrifugal or centrifugal, I think is often how it's called, force, which is not actually really a force caused by any kind of external entity to yourself, but simply because you have an acceleration, you're in a non-inertial frame. You're absolutely right. This is exactly related to that. And so the way we kind of went about this, I thought this would be a nice little way of illustrating what's going on here for those of us who are wondering what's this fictitious force business. I love my Einstein slide here, so I always have to work it in somewhere. So here's Einstein teaching us about relativity, and he's around 6 feet tall. I doubt that's actually even real, correct, but whatever. And the point though is this, is that if you want to calculate Al's height, we all know that you're going to take a change in y and you're going to find that you're going to get 6 feet there. And then we also know that if you were to change your coordinate system so that the origin is at his waist instead, then you'll say, well wait, his feet now are at -3 and his head now is at +3, and so what is his height now? Well, of course, as we know, if we take the difference in those two values, we're still going to get 6 feet. So we could say then that Al's height appears to be invariant under a coordinate shift. So all we really did is shift the coordinate origin from his feet up to his waist. But what can get tricky now is if you think about, say for instance, a transformation from one coordinate system to another that is something besides just a shift. So for example, consider if you have a coordinate system that stretches. So let's take these two spots that are just above and just below the origin. So this is a ½ foot above the origin, this is a ½ foot below the origin. And now what if we take our coordinate system and we stretch it? Then do we conclude that Einstein is really only like a foot tall? Something's weird about that, right? And so these are the weird things that can happen in general relativity because of the fact that gravity is itself, in a sense, a description of your coordinates. And as a result of that, you sometimes have to wonder, did I encounter a truly physical phenomenon, or is it just an artifact of my coordinate system? Yeah?
Isn't this another way of saying that in the cosmological expansion of the universe, the galaxies are moving away from each other, but the galaxies themselves are not changing in size?
That's true to a very good approximation. You're absolutely right, because the galaxies are very small compared to the cosmos as a whole.
Yeah.
So that would be sort of like these tick marks, right? These tick marks are where the galaxies are sitting, right? And so we have to ask ourselves, did they really have momentum when we looked at this coordinate system stretching there? One way of addressing this in a very concrete way is in Weinberg's cosmology. What you'll find is that he's also working with the geodesic equation of motion, and you might notice that he has this term here, which is the very term that we identified with Hubble Drag. But what you find is that that very term is in fact the term that could be applied not only to massive objects, but to non-massive, in other words, photons. And it turns out then that light is redshifted as a result of this exact term in the geodesic equation of motion. And we know that the redshift is a real thing that we observe with telescopes. So we know that the physics is correct. And as a result of that, since we know that cosmological redshift is correct and is real, we know that term is legitimate. So that was one way of us arguing what's going on. Another way of arguing what was going on is if you consider going into the boosted frame, and this is intentionally to make connection with Shiyama. Remember, that's what Shiyama did, right? He said that what I'm going to do is I'm going to move with a velocity v so that the universe looks like it's coming at me with a velocity -v there. And that's essentially what this boost here does. You're going to use this beta here, which is just velocity over c, to boost into some other frame, and then you have to transform your coordinate accordingly. So this is kind of like what I did with the ruler next to Einstein. This is a fancy tensor way of saying stretch your rulers, basically. Now when you do that, what you find is that the 0, 0, 0i and ij components of the metric transform as you see there, and in particular notice that you picked up an off-diagonal term there that you didn't have before. That's going to be especially important when we make the connection with Shiyama. Now if you consider the instantaneous rest frame of a particle, so in other words, kind of visualize that like we were just talking about that if I'm moving in this direction and the universe looks like it's coming at me, now let's use a measuring rod that's in my frame. So this is my ruler. So with respect to me, my ruler just stays right where I am. So my ruler is stationary relative to me. That's what this 0 here is telling me. And when you do that, you'll find then that you can write down your metric components in terms of that velocity that you're moving with there. Again, emphasizing this off-diagonal term that has appeared in the middle there. Now what we find is that we got to recalculate our connections. General relativity involves a lot of nitty-gritty calculation type stuff. And so when you recalculate your connections, do notice that this particular connection involves this time derivative of the off-diagonal. And remember, that off-diagonal guy is essentially what you could relate to a gravitovector potential. So there's something Shiyama-like hiding in here, which was kind of interesting to notice. The other relevant Christoffel symbol is shown there. And what you find is same force equation again. So whether you're in a boosted frame, in other words, whether you're in a frame where the universe does not look isotropic, or if you're in a frame where the universe does look isotropic, you find that you get the same force equation coming out regardless. So it's got kind of an invariance in that sense. Now what about the equivalence principle? It says that you can always locally transform into a freely falling frame where the metric becomes flat, Minkowski. So you can always basically make gravity go away, right? And if you're wondering how do you make gravity go away, well, mathematically, here's how you do it. You turn your g mu nu into an eta mu nu. Remember, eta is that flat space-time guy, right? And so you can always perform a transformation that achieves that. When you do that, then your force is going to go to 0. And so again, it might seem like a fictitiousness has emerged. But I can tell you that even when you're in free fall, it's not fictitious. That's my wife right there. She didn't expect that one. But that's okay, I'm with you, babe. So I can tell you that's transforming into a freely falling frame with your wife. There's nothing like it. It's a beautiful thing, I can tell you. Now,
Where is that?
oh, that's in San Diego. About a year ago.
Oh, wow.
Yeah.
Is it scary?
No, it's not too bad.
No?
It's not too bad. No. Yeah, it's actually pretty fun, right?
It's something that you have to get right the first time.
Yeah. And every time. And every time. Yeah, so imagine, for example, what if I had a box around me so that I can get rid of the wind and there's no other forces there, and let's say I have a coin and I release that coin. Is it going to fall away from me? This would be like my physics 2A question, for my students, right? Is it going to fall away from me? Well, if I'm accelerating downward at 9.8 and it's accelerating downward at 9.8, then no, it looks like it's just sitting there right next to me, which means that as far as I'm concerned, gravity is gone. There's no gravity, right? Right now, if I release a coin, it's going to obviously accelerate relative to me. But if we're both in free fall together, it's going to seem as if there's no gravity, right? That's essentially what's happening there conceptually. Now, does that mean that, in fact, there is no gravitational effect of the Earth on us? Well, here's wifey's world line, and here's hubby's world line. And when we're in free fall, what do you know? We come together. That took some PowerPoint work there, let me tell you. So, no, that was just so satisfying. I got to play that again, right? Okay. So, following our world lines toward the center of the Earth there, right? Now, did you notice this line between us shrunk? That line between us shrunk. And so, even though it seems like there's no gravity, because if I release a coin, it doesn't go anywhere, but there is something happening there gravitationally. And so that's described by what's called the geodesic deviation equation. So that distance, that black line that was shown between wifey and I is this symbol right there, right? That's the line between us there. And that's the rate, or at least the accelerating rate at which it is changing, right? And so if you put in the Riemann tensor components into this geodesic deviation equation, you do find that even in the non-relativistic case, there is a geodesic deviation. In other words, galaxies are really actually moving relative to one another. So it's not fictional, it's real, right? So that's another way of demonstrating that this isn't a fictional phenomenon. Now we got to get into the thick of general relativity. You're like, that wasn't the thick of it? No, we didn't actually use any general relativity yet, believe it or not. We just introduced a metric and looked at curved space-time. So what we find then, this is my traditional GR in a nutshell slide. Take your metric, we all know what that is now. Calculate some Riemann tensor components with it. From that, kind of apply like a dot product if you've taken a little bit of vector calculus, and get your Ricci tensor, and while you're at it, take a dot product again and get your Ricci scalar. From those, you can construct what's called the Einstein tensor, which is this capital G mu nu there. And from that, equate that to your stress tensor, and voila, you now have general relativity. Thank you very much. So this is my general relativity in a nutshell slide, right? Who needs a semester course when you can just stare at that thing for a while, right? So notice, of course, that the main point is that this is curved space-time encoded in this capital G mu nu. So that's the curvature of space and time. And this is your source, your mass, energy, momentum, everything that causes gravity to happen, like even Earth, for instance, causing our feet to be held to the ground. Now with that in mind, recognize that general relativity also requires conservation of stress momentum, which is written there mathematically in terms of the Bianchi identity. And so the idea then is this, is that if you break up this stress tensor into a component that is the gravitational field and a component that is the test mass there, what you can do is also decompose your metric into, again, flat space-time plus some perturbation, which doesn't have to be small. And you can evaluate your Einstein tensor in such a way that your linear order, meaning this to the first power, is inside this g mu nu 1, and then everything else that's higher order in this g mu nu 2 plus. If you do that, then notice that this term here you can replace with a kappa t mu nu, because that's just Einstein's equation, and then you can solve for this g mu nu 2 plus, and you can identify that as effectively your stress tensor for the gravitational field. So all that was basically to try to demonstrate the fact that the gravitational field itself has an energy density or energy momentum stress density associated with it. Now, what does that mean for us and our particle that we are trying to propel, at least that was our hope, with the RW metric? Well, it tells us this, is if you take this Bianchi identity and you work out just the momentum piece, which is the 0I piece, this is the momentum density of your test mass, this is the momentum density of the universe. And so it turns out that you can, in fact, exchange energy momentum between the two of them there. So an exchange is possible. However, unfortunately, it turns out to be dissipative, as I already showed. So this was an important formulation, because many times the objection is, how can you talk about exchanging energy momentum with the universe if the equivalence principle says that you can make gravity go away at any particular point? And the answer really, in my mind at least, resides in this integral. It's when you integrate over some distance, then you can see that there's a momentum loss. So you can picture it kind of like, if I'm moving along at one particular spot, I can at this spot right here go into free fall, and then it's like there's no gravity around me. But if I consider some distance and I integrate over that entire distance, there's going to be a momentum loss over the course of that entire distance that I would have traveled. So that's what that integral there is essentially telling us. Now, I'm sorry that that's bad news, because I would have loved to say, we found propulsion, we're going to all go to the stars. But that's kind of not what this is predicting, unfortunately. Now, on the bright side, though, we did discover something very interesting. In fact, Lance came up with a remarkable observation, which is that if you relate two frames of reference, one of the frames of reference being what he referred to as a beacon, so basically some object that's emitting light and moving away from us in the RW universe, what you can do is you can identify that there is a time dilation due to the Doppler shift. That's just the usual Doppler shift that you would have even from special relativity. But then you'll also have an additional shifting due to the Hubble expansion. And that's all encoded here. And what you can do is identify these as essentially the period of a photon, or in other words, electromagnetic waves, or light. And if you do that, then basically, and the only approximation I should mention here is that we are assuming the period of the light is much shorter than the time scale of the expansion of the universe. So in other words, your frequency has to be appropriately chosen. But the time scale for the expansion of the universe is like such a large period of time, you don't have to worry about that. Now what you find then is that there is a changing in the frequency of the light that you have as a result of all of this redshift effects due to Doppler shift, as well as due to Hubble expansion. And so if you map this out, it turns out then that the red shifting effectively decreases. So you'll notice, as it states here, this is a schematic diagram of the bluing of Doppler redshift. So in other words, you still have a redshift, but it's not as redshifted as it otherwise would be due to this Hubble drag that comes in. And so as it says, this diagram shows the time evolution of the locally observed Doppler shift of a receding beacon. This frequency shift at the beacon includes effects from time dilation, recession, and Hubble expansion. As it says, Hubble drag will slow the velocity relative to the cosmic rest frame, manifesting as a decrease in locally observed Doppler shift. Now, interestingly, this is where I thought it was quite remarkable.
Could this
Yeah.
Doppler shifts actually can be measured very precisely for astronomical objects. Could this be observable?
Yes, you are right on the track that where I wanted to go with this. So I'm going to come over to this slide right here. Yes, the answer to your question is yes. So if you look at the change in frequency that you would have associated with this effect, the local detection of cosmic expansion through time derivative of the redshift is essentially actually what you're asking about. So this is what you would have. You'd have an integral of this f dot from some emission time to some received time of your light. And it turns out that the Pound-Rebka experiment used a technique, sort of a Moss-Bauer type experiment, and obtained a frequency measurement of gravitational redshift to a part in 10 to the 15, which would mean, and that was obviously a terrestrial experiment. They weren't observing something astrophysical. This was right here on Earth, and of course there's a reference to that here. So the idea then would be, what they had is a tower, essentially, and they had an emitter and a receiver at the bottom of the tower, and they were able to use controlled Doppler shifts to cancel out the gravitational redshift over a 20-meter vertical drop, and hence demonstrate that there is in fact a gravitational redshift. So Lance had a remarkable observation in realizing that we could essentially do the same exact thing and just simply modify the formulation in the way that I just showed to demonstrate, in fact, that you can even measure the Hubble drag effect as well. So hopefully an experimentalist will pick this up one day. That's always what the theorist has to say at the end, right? Here's my theory. I hope some experimentalist out there will pick this up and do something with it and demonstrate that it actually happens. Now, lastly, I'd like to revisit the Shiyama approach. So let's go back to the whole idea of, I think actually my slide might be a little bit out of order. There we go. I have one slide here. Let's be moved over. Okay, so I want to bring it back home to the whole Shiyama approach. Remember what Shiyama had? A scalar potential that pervades the entire universe. And so what I conjectured was, if we want to demonstrate something that's Shiyama-like, what if we write down a metric of this form here? So it's only got this capital phi in there, which is like a scalar potential like Shiyama's was working with. And let's consider, for instance, that this phi naught is equal to c squared, so that this guy is actually just -1. And that this phi here, which is time dependent, is really just c squared a squared. In other words, if you put these back into here, you'll just get back to RW metric. I'm trying to sort of like marry RW metric with Shiyama approach, because Shiyama didn't use a metric theory of gravity. So this is my attempt at helping out what Shiyama did and putting it in metric form. Now if you go to the boosted frame, as you see, you pick up your off diagonal again, right? And here's the cool thing. It turns out that in fact, you can identify this guy as that gravitovector potential that Shiyama said you observe in the boosted frame. So it really does happen, even in a metric theory of gravity, if you just choose your metric correctly and you go into a boosted frame. Now, next, if you write down your geodesic equation of motion, but you introduce some external force, because remember what we're trying to do here. We want to see if I push on an object, will the universe push back, so that I can explain inertia. So this is me pushing on the object. This is hopefully the universe going to push back on me, which would lead to no acceleration. So that's what would happen. If I push this table, the table pushes back on me, nobody accelerates, but there's a force that's equal and opposite, like an action-reaction pair that would exist there. So that we hope would be encoded in there. Now, the boosted equation of motion in the non-relativistic limit turns out to be this guy here. Actually, I should say this is in the isotropic frame. This is when you boost, right? So you pick up this term here that Shiyama would say, aha, there it is. That's the induced gravitational field that you observe in the boosted frame. That's your inertia right there. In fact, let's go ahead and just set the left side to 0, because that's exactly what Shiyama does in his paper. He's like, let's just set the left side to 0. Again, picture it like you're pushing on a table, it's pushing back on you, nobody's being accelerated. What that would mean is that here's the external force, that's me pushing on an object, and here is the universe pushing back, this term right here. So it would imply, in bold, that the universe provides a reaction force which explains inertia. Hallelujah. Shiyama was right, we nailed it. Unfortunately, I'm not personally fully convinced that that's correct, because if you go back and you use phi equals c squared, which is what Shiyama used, and this vector potential definition, and our sort of RW metric in disguise, unmask the metric and bring it back to RW, is what I'm saying. Then what you find is that that same equation of motion I had becomes this guy right there. And notice that here's your external force, here's your Hubble drag, And here is essentially a coordinate acceleration. Remember the centrifugal that we were just talking about a little earlier? In other words, there's nothing actually there pushing, but it feels like there's something there because you're in an accelerated frame, right? So that's what this term here is, but just linearly speaking. Centrifugal is, of course, rotationally speaking. So what we find then is that this equation of motion reduces to what I have here, which I claim is really just Newton's second law in a boosted frame. In other words, it's exactly what you would discover, what you would have, say, like, on a, I don't know, in a Physics 4a textbook or something like that, where they would say, take Newton's second law and write it down in an accelerated frame. It would be this, right, where this is the acceleration that you have boosted into, essentially. So it's Newton's second law transformed. But of course, this is where the stuff hits the fan and where the debate rolls out and things start flying across the room because, because of course, this predicts that we did not explain inertia as we expected we would. So here's my conclusion then, and it is a tentative conclusion. I'm not saying that this is the end game, but here's my tentative conclusion. General Relativity and the Robertson-Walker cosmology predicts that there's an energy-momentum exchange between test masses in the gravitational field of the universe. It is not prevented by the equivalence principle. That was good. Now, the energy-momentum exchange is always dissipative. It can't be used for propulsion. That was bad. Inertia is not explained by the RW cosmology of Shiyama's approach, even when we cast it into a metric theory of gravity. Again, kind of bad. But, as a fun little side note, there's a possibility for experimentally observing the Hubble expansion of the universe locally in a Pound-Repka type experiment.
Yeah. Might it also be a nice way to test the equivalence principle itself?
How so?
To
see if it's violated?
Yes.
Yes, that's true. If in fact we can pull this off, then I think we could pull this off. But I imagine there must be a whole assortment of ways to test the equivalence principle in addition to this particular one, but yes.
Yeah, but every 5 or 10 years or so, somebody from either NASA or the European Space Agency proposes to put a spacecraft, to do it with a spacecraft. And the proposal is always shot down because it's too expensive. Spacecraft are expensive. You could do it.
I'll take that question in just 1 minute.
Well, what'd you say?
Oh, someone keeps saying hello, hello, and I told them we'll take the other question in just 1 minute.
Well, the thing is, various teams in NASA and elsewhere keep proposing a spacecraft experiment, an experiment across the spacecraft, an experiment on board a spacecraft to do this. And it's always shot down. Other things are found to have higher priority. A big reason being a space experiment is really expensive. If you could do this in the laboratory, that would be a big deal.
That is very true. That's very true. For sure. Because, and especially since the apparatus has essentially already been set up. Now, I wondered, by the way, and I mentioned this to Lance, I wonder if we could even look into whether the experimental setup still exists, because I know it was quite some time ago that the experiment was actually done, the Pound-Repka experiment. How long ago is the paper? It was on this previous slide. As far as, I think it was, here we go, 59. It's been a while. Oh, you remember that?
Yeah, I was
Such a good memory.
like 2 years old.
Yeah, it's been a while. So I don't even know if that might still exist. And also, they probably have to modify it because now you have to have an object moving while it emits, right? So that it's experiencing Hubble drag as it emits, so that this modified Doppler shift could then be experienced. So it would have to exist, and it have to be modified, or someone would have to do it from scratch. But you're absolutely right. I'm sure it would be far less expensive than the types of space-based type experiments that have been proposed. You're absolutely right.
See in the chat box there was some.
This is Ray Chow. Hi.
Hi, Ray.
You're asking me, but let me ask a question. Can you hear me?
Yeah, my volume's really low for some odd reason, but I do hear you well enough that I should be able to.
Okay.
Want to go ahead?
I have a comment about the experiment, the Pound-Repka experiment. You should think about performing it in a drop tower such as the one in Bremen, Germany, where you drop a absorber or emitter of Mossbauer radiation from a drop tower so that it accelerates as it falls. It will then maybe be able to detect this new effect that you and Lance have been working on.
Absolutely.
Okay,
So Ray was talking about that there's a drop tower in, did you say in Germany?
Yes, in Germany, in Bremen.
Great. The original Pound-Rebko experiment was in Harvard. They basically,
Yes.
it was like a Mossbauer effect where they basically shot gamma rays from the top of the tower to the bottom of the tower.
Right. That was a stationary experiment in that the height of the tower was held fixed. But as I understand Nathan's and Lance's calculation, you have to have a drop tower to see their
Yeah,
effect.
you're right, Ray.
Is that
We would
right?
have to have a drop tower, and it would also have to be set up for the emitter to be able to fall freely and be able to observe the light from that emitter while it's dropping, right?
Oh, yeah. Well, it's. I haven't done another question, if you don't mind.
Yeah.
There,
You have another question?
Yes. You know that there's been observations not only of the Hubble expansion of the universe, but of the accelerating expansion of the universe. That won the Nobel Prize. Saul Perlmutter worked on that. And so
Ray's commenting on that it was not just the Hubble expansion, but the accelerated expansion of the universe that led to a Nobel Prize winning.
Yeah, the question is to you is how do you account for that in the Robertson-Walker metric?
And how would we account for that in the Robertson-Walker metric? Isn't it associated with the rho critical? Like essentially, I think it's on the right side of Einstein's equation in the source term, I believe, where.
Nathan, I could answer that.
Oh, Lance is chiming in.
Yeah, it just affects the parameter A. So you put in your energy budget of the universe at 70% dark energy, 20% matter, and you just get a function of A of time. So that's how it comes in. And we didn't specify A sub t. You can see A is just a variable here, or a function that's not specified. It actually comes from the Friedmann equation, and that's where
it makes a lot of sense. Lance is pointing out that it's ultimately going to be associated with the A parameter, which we didn't specify. We left it general. And so that A parameter, which appears there, for instance, in that expression at the bottom, would take into account the accelerated expansion. And so it would be encoded there in that final Doppler experiment.
Yeah, but there's a piece of physics missing because the accelerated expansion indicates a kind of anti-gravity, a repulsive gravity on the scale of the universe. And how do you account for repulsive gravity in the Friedmann, in the Hubble expansion?
It's built in. It's built in to the Friedmann equation. So, the dark energy, it has positive energy density, but negative pressure. So, I don't know if that's anti-gravity, but it's negative pressure. But still, the energy density is positive. You know, it's contributing to the curvature of the universe. It's 70% of the critical density.
Okay, thank you.
Yeah. I had also a comment, Nathan, but are we running long? Do we have to cut off?
No, we were actually just trying to adjust our volume on our end. Oh, there we go. I think we can hear you better now.
Okay.
Oh, that's so much better. Now I don't have to like reiterate everything you say.
Yeah.
So
I just had a couple quick comments. Back on Einstein 1, 2, 3, that was just a Lanceism. I just called it Einstein 1, 2, 3. But Einstein did enumerate them in that 1921 paper, and people copied that enumeration. But as it's written there, Einstein 1, 2, 3, no one would know what you meant by that.
Oh, okay, yeah, I did wonder if that was very popular or.
And also, Cephalini and Wheeler did their stuff in the 90s when they considered, their explanation for inertia.
Yeah, I know it's a very rich history that I didn't do nearly justice to as I would have liked to. since we obviously have an hour and we're trying to jam in quite a bit.
But there's one more piece of physics, so important physics, about the fundamental question again, of course, we came up with the null result, but Shiyama had a physical assumption that we did not address and we still have not thought through, which is he set the whole momentum, the momentum from the whole part of the universe is zero. So he's like setting the geodesic equation to zero in our terms, and then you get this induction. I'm not sure we've thought through that or tried to do that. So just to give Shiyama just a bit of credit there's a crucial assumption he has, so that you can get inertia as the inductive effect by setting the left-hand side, so to speak, of the geodesic equation to zero.
Yeah, I did address it to some degree. You may have possibly noticed here near the end of the talk when I mentioned on this slide here that if we set the acceleration on the left to zero to attempt to explain inertia, then it would seem to imply that we found the reaction force of the universe.
Just a reminder, Nathan, the people on Zoom can't see your laser pointer.
That's right. Thank you. So, yeah, this equation here, did you notice there that we set the acceleration equal to zero?
Yeah, I mean, it's sort of a keystone assumption, and I think it's good to have it there. But that was what the key step for Shiyama to do, which is not in the geodesic equation.
Right.
It was not in any of our considerations. And what the physical meaning of it is still to be determined, or maybe it has no meaning. But I just wanted to highlight that that key piece is still not addressed in our framework.
You're absolutely right. In fact, it was really actually kind of at this slide, right after the Pound-Repka experiment discussion. The rest of this is sort of like Nathan's speculation, Nathan's way of trying to connect back in the Shiyama stuff. So as you just mentioned, Lance, it wasn't formally in our published paper, and I gather from you that you felt that we haven't really even addressed it well enough yet.
Oh no, what you've shown is separate. I'm not talking about that. I'm just saying, in our work, in your speculation, subsequent anything at all, we did not kind of tackle this keystone assumption that Shiyama made that the total momentum is zero.
True.
And I'm just saying, to really put it to bed, someone needs to think through that. I still am not sure what it means, but what you've done here is fine. Your follow-on work is fine. I was just talking about something that none of us have really addressed at all.
Yeah, that makes sense. Maybe in a future paper.
Hi, Nathan. Can I ask you one very quick question?
Yeah.
So I have to confess that I have limited knowledge in this field. But so you talk about Shiyama approach. It uses gravitational field. I think that's in the boosted frame. But what's your take on some experiment of changing gravitational wave into electromagnetic waves, like dissipation, layers, conversion?
Oh, well, I love that topic, but I couldn't possibly do justice to it, right now, since gravitational waves, of course, have not been included in this topic. So, but just so I gather your question well, you're saying how would we look at the conversion between gravitational waves and electromagnetic waves in a boosted frame?
Yeah, boosted frame or like general experiment. What's your take on that? Like, what do you think on that experiment?
It's actually kind of funny that you mentioned that, because there was something I came across while working on this paper with Lance, and I included it in emails between all of us, but it probably got lost in the shuffle because we have a bajillion emails all the time between all of us. But one of them was this so-called super co-moving coordinates. I don't know if anyone here remembers this. When Bertschinger was saying, when we were reading Bertschinger's work about the fictitious force business, which made me a little concerned that we were overlooking something, it led me to look at this whole idea of super co-moving coordinates. And evidently you can make the Hubble term, you can eliminate the Hubble term, the Hubble drag term here, while leaving other terms. So it's not like a full-on coordinate transformation back into free fall where everything goes to zero. You just eliminate the Hubble drag term. Now, interestingly is this. It turns out that the gravitational wave force also is a term that looks just like that. It's velocity dependent and has a minus sign, just like this. I even facetiously refer to it as a gravitational wave drag force. And so you can actually remove that also from the force equation. So I think the moral of the story really is that you're really best off working in terms of, say, the geodesic deviation equation, because that's where you know you have something physical, like I was referring to right here on this slide. There is nothing that will take away this L dot dot at the bottom of the screen there. No coordinate transformation will remove that because it's in terms of the Riemann tensor, which is coordinate invariant. So I suppose my simple answer, at least the best I could do just on the fly right now, would be that even if we're looking at the conversion between gravitational waves and electromagnetic waves and things of that sort, I would suggest the geodesic deviation equation is the best way to avoid any kind of coordinate artifacts associated with free fall or boosted frames or any of that.
Right, thank you.
You're welcome.
Can you go back up to 44 or 42?
Oh, 44, you want to see me?
Oh, okay. Oh, no, so I get 42. Oh, no, okay, 42. Okay, so there the force equation is minus 2 hv plus h k squared v cubed.
Oh, that's a typo. That's
okay,
right.
okay. So it should be minus, right?
Yep,
Because
yep. Thanks for catching that. Should be a minus there. Can't get away from the drag. Thanks for catching that one.
Okay. And the other thing I was going to ask.
I think the sign was right.
Well, it's different above. So in one place it's definitely wrong.
I know that, oh, no, it's minus in both. I think I know what you're thinking of, Lance, which is that in the paper when we actually wrote it, what we found was this. So this is the actual paper itself. And when we first worked out the equation of motion, we arrived at this equation right here, 16. And when we looked at 16, we're like, oh, okay, that's Hubble drag, not so exciting. And then we're like, well, what about the fact that these are technically actually 4 velocities, not coordinate velocities? So it's kind of like the little gamma, if you wish, you can think of it as, is hiding in there. And so we worked that out carefully then, and Lance pointed out there in equation 17 that you can show that the entire force is in fact negative definite, as you see there. And then that's what can be written in the cubic form, which we didn't do it in the isotropic frame, but if you go down to equation 43 of our paper, then you'll see that in the boosted frame, we did write it out explicitly. It's in equation 43 here. I think actually...
Yeah, the sign was right, though, Nathan. If you back on the first equation, you can see that it naively, it looks like an acceleration, but you do a little math and you find out it's negative definite.
It's negative definite. And then what happened in equation 43 is, I should point out that in this paper, when Lance wrote the coordinate transformation, he boosted with a minus v here, whereas I chose to use a positive v. Yeah. Do you see it there in equation 32?
If you scroll up to where you first dove in here, I think, that's where I thought that we were correct. You're saying you had an overall minus injected.
I get an overall minus no matter what you do.
Yeah, keep going. I think you're almost there. It's just where you were before you jumped out. Oh, well, it doesn't matter.
I think you must be talking about the equation 16, 17, 18 discussion.
Yeah, there we go. Yeah, you can see that, naively there's a plus sign there, and I thought the same thing too.
Yes.
Oh, great, we got a plus effect, but then I realized it was negative definite because you have to use the invariance of the length element.
Yes.
So, yeah.
Yeah. So it
That's
looks.
why it looks like what you had on the slide looks like equation 17 to me, but I guess you're saying, well, I have a minus sign in there on the v or something.
Exactly. I wrote the whole thing up a little bit differently on the slides on purpose because I felt that the natural thing was to just simply boost in the positive direction and then discover that all the force terms are negative. I felt that that might be a little bit easier to see what's going on. So you'll notice that my transformation there at the very top of that slide there involves x minus c beta t. So I'm boosting in the positive direction and then arriving at a force that's purely negative. Yeah. So any way you cut it, you're not going to get momentum out of the universe through this mechanism, is what.
Yeah. I think that equation is still wrong, though, Nathan, with that minus sign there, for what it's worth.
Okay, I'll check it out. I'll check it out more carefully. Yeah.
Okay.
This is all in the linearized weak field approximation, which works for gravitational waves, which you like, and also works for the Mach's principle, dealing with mass across the universe. But I might suggest, have you ever done anything with the strong in the strong field?
That's a great question. So Dr. Ringwald is asking, he's saying, it seems that all of this is being done in a weak field limit where we have a small perturbation. I'll apologize that I moved back and forth between those in this for a reason, by the way. Up here, I used the weak field limit just to help us understand Einstein 1, 2, 3. So I used the weak field limit right there. And then we talked about, Jim, and then we introduced the paper. But you'll notice that right here, when I start talking about the paper Lance and I wrote, I am actually using, it's right here. Do you see that guy is actually higher than first order? So these connections are actually full, they're exact. And so this is all the terms that you get there at the bottom there in the force equation. If you were to state a first order, with the RLW metric, you actually won't get anything, interestingly.
Because it strikes me as potentially an interesting way to accelerate quasar jets.
Oh, I don't know anything about that.
Well, common observation with both big black holes and stellar mass black holes are jets coming out of them.
Yes.
And jets are not supposed to things are not supposed to come out of black holes. They're supposed to go in. So whenever you show this and people point this out, you say, well, it's not really the black stuff, it's not really anything coming out of the black hole. It's because the black hole's presence causes sufficient warping of the space-time and the inner accretion disk to collimate a jet.
Yeah.
But when you ask them exactly how this works, they start muttering about magneto-centrifugal acceleration and relativistic tornadoes, which is code for I don't know. So this potentially might be okay. So you might not get a Starship drive out of this, but
right.
You might get a way to accelerate quasar jets out of black holes.
Well, it's a braking mechanism. So if you want to slow down the quasar, maybe. It's a braking mechanism, but it won't accelerate its rotation.
Black holes are typically observed to be rotating at a very large fraction of their theoretical maximum.
Mm-hmm.
They're nearly maximally spun up.
Yeah, yeah.
So if this is a drag force, that would work against that.
True. That is right.
Yeah.
It would. But do keep in mind, of course, that the time scales or length scales, if you wish, are cosmological level. So you have to wait millions and billions of years for these effects, or have tremendous sensitivity, like in the experimental approach that we were talking about down here. What happens is with the Pound-Repka experiment type approach, you're making up for the smallness of the effect by your tremendous sensitivity because of the Mossbauer type phenomena that you have. Yeah.
In other words, you need a very precise experiment to see this effect at all.
Yes, that is very true. 10 to the 1 part in 10 to the 15, for instance. So again, I also needed to give my acknowledgements. So I do want to thank Dr. Lance Williams, Director of Confluence Research Institute, for kindly inviting me to participate in the research with him that led to these results. And I also want to thank Dr. Jim Woodward. I think maybe he's not on the Zoom meeting anymore, possibly. But I do want to thank him for the very inspiring conversations that we've had together on this topic. And then I want to also thank Fresno State for inviting me to come and share this research as well. And so I'm always very appreciative of the chance to be able to be here to speak. So please invite me again one day if I have something meaningful. So thank you very much.
Thanks, Nathan.
You're welcome.